Vanakkam. Welcome to this course on biomedical instrumentation. In the last week, we looked at pressure measurement and body temperature. In this week, we will look at flow measurement. What do we mean by flow? What is the thing or the fluid that flows in the body? We know that is blood. Why are we interested in measuring the flow of blood? Because it is a critical measure of health. There are different types of flow meters, and in this video we will discuss the measurement of flow and volume. What is the difference between flow and volume? Flow is unit time rated volume, that is how much quantity of a substance or a fluid has flown in a given time. Volume is the total volume that has flown. Right. What are the types of blood flow measurement techniques? In this video, we will introduce one type of these measurement techniques, namely the electromagnetic flow meters. What are we interested in? We are interested in movement of blood through a blood vessel or a tissue or an organ. Specifically, we are interested in measuring the volume of blood that flows per unit time, per second, per minute, something like that. Why is this a big challenge? Because blood vessel diameters can be several centimeters to less than an mm or several mm's in size. So, there is a huge variation in the size of the blood vessels of interest. Also, the velocity of flow varies depending on where you are making the measurement. So, there is a wide range of flow velocities. There is a need for high sensitivity, high accuracy and reasonable amount of stability to make this measurement. So, there is a variety of blood vessel sizes. For example, the aorta is very big, then the capillaries are really small. Velocity of blood flow is high near the heart. Obviously, it will reduce. Why would it reduce? Because there is a resistance offered to flow by the blood vessel itself. Modeling the cardiovascular system and understanding the physiology of the cardiovascular system is beyond the scope of this course, but just reminding you that velocity will vary depending on where you make the measurement. So, there is a need for high sensitivity, accuracy and stability. There are different types of flow meters that are available. One of them is the electromagnetic flow meter. The other uses ultrasound, and in this there are different types. Transit time flow meter, one measures the amount of time it takes for the sound to travel in upstream and downstream. Depending on that, it essentially estimates the velocity. The other is the continuous wave Doppler flow meter. In this case, what is measured is a frequency shift. Doppler shift means a frequency shift. Recall from high school physics what is the Doppler effect. Then, but the Doppler effect, Doppler shift or the continuous wave Doppler flow meter will only measure the flow, but not the flow profile. Let us say I am interested in measuring a flow profile. What is the difference between flow and flow profile? Profile indicates where in the blood vessel what is the velocity. This is a profile, for example. Let us say I am interested in measuring the profile, then I can use a pulsed Doppler. They have classified laser Doppler flow meter within ultrasound, but laser Doppler flow meter essentially is a separate type of flow meter that uses light, monochromatic light, that is what is laser. Then thermal flow meter, there is a heater that is placed, and depending on the mass transfer that happens, the amount of heat that will be carried will also vary. How much blood flows, that much heat will be carried by the blood, or that much heat will be lost by the heating element, for example. That is the principle. So, these are the various types of blood flow meters that we will look in the forthcoming videos. In this video, we will continue our discussion on electromagnetic flow meters. Electromagnetic flow meter essentially works on Faraday's law of electromagnetic induction. Recall what is the principle of operation of a dynamo. What is the principle of operation of a dynamo, or say a car power generator or an alternator in a car? Essentially, there is a magnetic field, copper wires move, copper coils, copper wires move within the magnetic field, and they cut the lines of magnetic flux. When that happens, an EMF is induced in these copper cables, is it not? And what is the principle? The principle is that the amount of this EMF depends on the magnetic field itself and the rate at which this alternator is, or the dynamo is, breaking the magnetic flux line. So, the velocity comes into the picture. This is what happens in a car dynamo or a car alternator, but in this case we are interested in measuring blood flow. In this case, it is the blood that is acting as the conductor, the blood acts as the conductor, and so voltage is induced when blood flows through a magnetic field. So, a magnetic field is kept perpendicular to the blood flow, and in the third direction you try to pick up the EMF. Is the blood a conductor? The answer is yes, because blood is essentially an electrolyte that contains ions, positive and negative ions. So, it is essentially a conductor, it acts as a conductor and it breaks this lines of magnetic flux that is offered by this electromagnetic flow meter, by this electromagnet, right. So, that is the principle. So, for example, this is a one type of flow meter, this is another type. So, the principle is the same. So, there are these magnetic flux lines that are there, and flow itself is in this direction, and I am measuring the EMF. This is of interest for me. So, note that the conductance of blood is comparable to the conductance of saline, comparable to the conductance of saline. I can write the induced EMF E as E is essentially integral 0 to L U cross B vector dot dl. This is the real formula for the induced EMF, where what is U here? U is the velocity of flow, in this case velocity of blood flow. What is B? B is the magnetic flux density, and dl is the distance between the electrodes. and not. In this case, velocity is mentioned as v. So, E is essentially the product of the magnetic field B times the velocity v times the diameter of the artery d. Right. If I simplify that, that would actually become E equal to BLU under some conditions. What are the conditions under which this will happen? When the magnetic field is uniform and when the flow is uniform. You can assume that the magnetic field is uniform because in a small space this electromagnet can produce reasonably uniform magnetic field, that is this, but is it a reasonable assumption that the flow is uniform? Uniform means within the blood vessel flow is at different points along the diameter of the blood vessel, flow is or the rate is exactly the same. Is that a reasonable assumption? No, but we can make this assumption. So, also one more thing to note is that these electrodes that are picking up this E are relatively small. So, that component of flow near the electrode contributes more to the EMF than those components of flow that are farther away from the electrode. Okay. Because electrodes are small, electrodes are not really big. This formula assumes that the electrode is very big when compared with the flow. That is actually not true. So, there are practical problems. The other is if the flow is axisymmetric, then there will be some, these assumptions will become true, but when will the flow be axisymmetric? If the flow is laminar, then the flow will be axisymmetric, but if the flow, for example, near the curve of the aorta and some of its branches will be asymmetric. Now, I will not have flow that is uniform. So, there are several assumptions that I am making here in this. If we know the cross sectional area of the blood vessel, then I can find the average velocity, but then there are some assumptions. By the way, the cross sectional area of a blood vessel depends on, it is not a constant. We know that it is not a constant, in particular for arteries, depending on which cycle, which part of the cycle the artery is in, depending on that the diameter will vary, but we are making this assumption. Okay. Now, velocity is essentially the flow rate divided by the area of the conductor, area within which this flow is happening. So, the voltage is directly proportional to the flow rate, but then I am assuming several things. I am assuming smooth symmetric flow. This is rarely the case. So, there are several assumptions, that is okay, but still it might have some specific applications in this field. So, these are some of the relations of interest. It is quite these relations are self-explanatory. The induced EMF E is essentially the product of the magnetic flux density, the velocity and the diameter d or size of the, and the velocity is essentially the flow rate divided by the cross sectional area. And so, I could essentially relate the EMF to, substitute for V as Q by A in the relation for EMF, I will essentially get this BQD by A. but then A is pi r squared, where r is the radius of the blood vessel, but that is d by 2, where d is the diameter. Note that this d is different from that d, or no, these are the same d's, right? No. Now I could substitute for pi r squared as pi times d by 2 the whole squared, or pi d squared by 4. Substitute for it, I will essentially get the induced EMF as 4bq divided by pi times capital D. So, while designing the flow meter, it is critical to consider some things, that the tube must be non-magnetic and must be lined with sufficient insulation. Electrodes must be made of stainless steel or platinum, preferably non-polarizable electrode. Even if you use non-polarizable electrode, if you use DC to power, there will be electrode potential that will get developed. We will see in future classes when we discuss biopotential electrodes what an electrode potential is. Even if you use a non-polarizable electrode, there will be an electrode potential that will get developed. And so, the net output that you are measuring is essentially the sum of the electrode potential and the potential that is caused due to the blood flow, something to keep in mind. If you use DC, there are problems with the DC flow meters, which is why it is better to use AC flow meters. We will see that in future slides. So, you need to size the slot or the probe to fit exactly around the vessel. Now, that means that for different vessels, I will have to have different flow meters. I will need n number of flow meters, because because vessels come in different sizes. For iron core, you use these sizes 1 to 8.2 millimeter size, and if the size is greater than 8.2 millimeter, then you use air core. Two types of flow meters we discuss: sine wave flow meters and square wave flow meters. This is the example of the square wave flow. This is the square wave and this is the sine wave flow meter examples. So, there are two of these types of electromagnetic flow meters itself can be classified further into sine wave, and the ones that use sine wave and the ones that use square wave. Essentially, sine wave flow meters use a sinusoid, an alternating sinusoid to generate a magnetic field, and the induced voltage is also sinusoidal, right. But there is a problem. The problem is that this usually induces a transformer voltage, and the transformer voltage usually is several times the size of the voltage of interest. Now, how to overcome that? Now, that is something that we will need to look at. But it yields excellent signal to noise ratio, but it has requirements of phase shifter, phase stability problems. Some stringent controls of phase stability is required. So, this transformer voltage that is caused because you are using a sinusoid around and you are sending this across a copper coil, there will be a transformer voltage that will be generated, and this transformer voltage is usually several times the magnitude of the voltage of interest. That means, and that is naturally created, and it is not easy for you to eliminate this. There are several ways in which you can overcome that. This essentially causes a baseline drift, not by a small amount, a huge drift usually, and there are different ways of eliminating this. One is using a gated amplifier, the other is by using a phantom electrode, splitting an electrode into two and keeping one of them farther away to measure the transformer potential and then eliminating it. The advantages of the sine wave system is that it is highly accurate, and it can measure in both directions, and the range of flows that it can measure is relatively wide. In contrast, in the principle remains the same. So, there is a magnet and there is flow that happens across the two poles of the magnet, but what do you use to energize the magnet? That is the question. The induced voltage in the magnet, if it is a square wave, then the transformer induced voltage appears as a distinct spike. Now I can easily separate the transformer voltage from the flow signal because it has a specific spike, and so it has very specific gating of amplifier. The advantage is that it has reduced interference. So, transformer voltage interference is highly reduced, and you have great control over energizing currents magnitude and waveform, and the signal to noise ratio is relatively high and the accuracy is very high. With this, we come to the end of this video. In this video, we looked at what are the types of measurements that we can use, or the measurement techniques that we can use to measure blood flow, and we looked at electromagnetic flow meters. With this, we end this video. Thank you very much for your attention.